So this is the summer, if you haven't realized that, which means that things have to move necessarily a little bit faster. What I would normally do at this point, today would be about the autonomic system, and the next week would be about the endocrine system, if we had enough weeks. I had to make some decisions about where to compact the course a little bit to get everything into 10 weeks. And one of those choices I made was to put the autonomic and endocrine system chapters together. We're going to do both of those today. Basically, I'm going to talk about the autonomic system this morning, first half today, and then endocrine system the second half. For the autonomic system, I want to illustrate how that works by looking at a clinical example, a case study. So that's what we're going to do this morning. And in explaining the case study, hopefully I'll explain some things about the system. And then for the endocrine system in the second half today, I want to concentrate on looking at micrographs of endocrine glands, and through that, talking about what they look like under the microscope. I'll also talk a little bit about how the endocrine system works. So that's the plan. It's a little truncated from what I would want to normally do. I'd rather have a full day for each of those systems. It's just not going to work that way. So I would encourage you to look to earlier material that I've saved. And let me just remind you, in the syllabus, after the schedule of topics part, there's a section that says online resources, and there's a link in the middle. I haven't updated how I've written this section. The links, though, are the really important part. So there's a link to the YouTube channel that I've created, where I'm capturing what I'm doing here on in the lecture. For example, last week, these two videos right here are introduction, how the class works, the first half of what we did, and then sensory systems was the second half of what we did. So that's last week's class. You can go back through this material and find recordings of other classes from last semester. If you hit the load more button at the bottom a few times, you'll get everything in my channel, which goes back to February, when I started doing this. And it's mixed in. There's some A&P1 and A&P2 stuff. So for instance, these two on chemistry are from A&P1, for example. This is about the endocrine system lab. This is the autonomic system case study. Kind of hoping there'd be a little bit more. It's right around when I was doing the autonomic and endocrine systems last year that I was starting to do this. So I don't seem to have any additional lecture material on that in the YouTube channel. Also in the online resources, there's a link to audio recordings of stuff. It says Google Drive just because that's the source that I'm using for that. And it'll load in a second. Here we go. If you go to this page, it always starts by showing you these big icons, which is really kind of annoying, I think. So it's easier to switch to the list view. Then you can read the full titles of the recordings. Let's see. So these are organized in chronological order because the file number starts with the date that it was recorded. And so the earliest recording, which would be June 2014, so last summer, starts here. So you can see what I recorded. Again, this is just audio recording from last summer, and then you can move up to, here's where September is, and this is going to be a little bit longer. Here we go. Presentation, autonomic system here, more autonomic material here. So you can listen to those if you want to get a bit more material. As the semester progresses, the YouTube channel will have more coverage of the material. It's just, I started kind of a little bit after the beginning of the semester. So apparently I don't have the recordings, the full recordings for the autonomic system lectures. And I think the lecture version of the class where I would have gotten that, the computer there, I was having some trouble getting this recording thing. So I didn't get any recordings of that early stuff there. But I want to point that out, some material you can go to. So, we're in the autonomic system, which is your unit 2. Again, the second half of the day, we're going to be in unit 3, which is the endocrine system. I'll come back to this. I want to go into the reading assignment and point out some things, which I'll get to later. So I just open that link up. But I actually want to go into the practical folder real quick. I'll talk more about how the practical works later on in more depth. But one of the aspects of how the practical works is it's built around case studies. It's built around clinical examples. So this is what you'll see. The 4 things that you just saw there, one of them is hidden because I don't use it all the time. But there's a link right here that says practical 1.2. That's practical 1 for AP2. And the A designation is just because I have 2 versions of it, and the hidden thing is the other version that I'm not using. And then it says cases. And this goes to a document that has case studies that are necessary for you to familiarize yourself with for taking the practical. And part of the process to get you familiar with this as a teaching tool is what we're going to do this morning. So we're actually going to look at the first case study here, which has to do with the autonomic system. And I want to kind of model for you how the case study approach works for this class. And you'll be able to take that and look at the other cases and prepare for the practical when that comes up later on. And I'll give you more specific information about how the practical works when we get closer to it. But for the sake of today's class, we're just going to look at this one case. Now, we'll come back to the case in a second. I just want to talk a little bit about what I expect you to get out of the case studies. Now, the point of the case study is for you to understand how the basic anatomy and physiology of what we're learning in this class relates to real-world situations. And so I have kind of a framework for how you should approach a case in this class, and it'll help you get the information out of that case that you need. The case we're going to look at today is actually quite short. There we go. It's just these 2 short paragraphs here. But it has a lot of information that we can get out of that if we sort of approach it the right way. So the first thing that I expect you to do as you're looking at a case is to be familiar with the terminology, which at its most basic is that you understand the definitions of all the words that are there. We're going to be reading this case study here today. And what I would normally do, or what I used to do, is I'd say, underline any terms that you don't understand in the case. And as we discuss the case today, I'll help define those. Nowadays, I don't necessarily have to give that instruction because most of you have access to the internet right now, whether it's through the laptops we can see here, or a phone or a tablet or whatever. So most people can search for definitions pretty quickly. But we'll talk a little bit about the terminology in this case when we're discussing it. But also in talking about a medical case, besides just plain definitions, you also have to be familiar with what I want to call jargon, the more formal language of medicine. The example I like to use for this, which is not the perfect example of it, you might know what the word blood means, might know what the word pressure means individually, but as a term, blood pressure means something very specific. You probably know what blood pressure means also, but I just wanted to illustrate that idea. So if there is something like that that's specific to a formal medical presentation like this, you need to be familiar with what that means. And so for something like blood pressure, when it refers to that, if you don't already know it, you should also, as you're going through the case, make sure you look up what the expected values for that are. If those are, if that's information that's provided in the case, it's probably relevant. And so you want to understand what might be different between the data presented in the case and actual values or normal values. So pay attention to that sort of stuff. And then finally, also, abbreviations are important to understand. In medicine, a lot of abbreviations are used, just it's a nice shorthand for a lot of things. The problem is that there are more abbreviations, no, I should say that differently. There are multiple things that certain abbreviations can stand for. So be sure that when you see an abbreviation, you look it up, and be sure that what you learn for its meaning is relevant to the case. Don't just say, oh, I found this abbreviation, and write that down. If it isn't the abbreviation that's relevant to the case, then you haven't learned anything. You haven't gotten the appropriate information. So pay attention to that stuff. So approaching terminology this way is just to make sure you understand everything that's in front of you. Now, the case that we're looking at today is actually pretty simple. So this isn't probably going to be any big problem for anybody. But then as you're reading through the case, it's basically a little story. Guy goes to a doctor, says, doctor, we got this problem, and sets up the response to that. From that, you should be able to pull out a list of the symptoms and signs of what's going on. So I don't really care about the finer detail of what the word symptom or sign actually means, but collectively what I'm referring to is really the functions that are lost. What's not working for this person? Yeah, I'll just stick with that. There's something more I'm going to say about that, but I need the specifics of this case to address it. Okay. And with those symptoms and signs, then you want to look at the systems that are involved. Okay. So the organs, or I should say organ systems, affected in the case, or where functions are lost. Now, another way of saying anatomy and physiology is structure and function. So really that's what we're talking about here. The systems are the structures that are affected. The symptoms and signs illustrate the functions that are lost. So in looking at that, we're really looking at the underlying anatomy and physiology that the case has to do with. Okay. So that's sort of the framework I'm saying that you should approach these cases with. Now, what we're going to do today is I'm going to give you some time to look at the case, and I want you to approach it in this way, and then we're going to discuss the case really within this framework to set up understanding more about the autonomic system. Okay. So let me just enlarge this. Several of you have access to this, and Google has these little anonymous icons for people that are logged in. So you might have it in front of you there, but for those of you that can't get it pulled up in front of you, here it is on the screen. Just these two paragraphs here. Don't worry about case 2. So let me just get that off the screen. Yeah. So I'll give you 5 minutes or so to read through this and make sure you understand the terminology, come up with a list of the symptoms and signs that you see there, and think about what systems are involved there. So go ahead and work on that. Okay, looks like everybody's had a chance to look through this. So to begin with, is there any terminology that people were unfamiliar with? Okay, yeah. So in this one, actually, I kind of put this word in specifically because I didn't think a lot of people would recognize it. But otherwise, the case is pretty straightforward. Now, we can break this word down and kind of understand what it means pretty easily. So it starts with the prefix a, which when we see that in a word, it's usually a negative. Okay. And then the root of this word is whoops. Oh, shoot. The root of this word is FEBR. Okay. Now this comes from Latin, and when we have a Latin word, we can often, sorry, I should say that. We have a Latin root in a medical term like this, we can often find common English words that come from that same root. And in fact, this root is a cognate for an English word that you're probably very familiar with. And it's very easy to see what that is if you understand one little thing about languages. In Romance-based languages, which would be things that are derived from Latin, Romance as in the Romans, B's and V's are kind of interchangeable. And especially if you're familiar with Spanish, you've probably seen that before. Something spelled with a V, but it's pronounced like it's spelled with a B or something like that. The two letters are kind of interchangeable. So for this root, FEBR, the English cognate that comes from that, just has that B switched for a V. So what does that root mean? Fever. Fever, right. So afebrile means without fever. Now, there's actually a couple of ways to say this in a case, and the other ways I might have said it would have been a little bit more common language, but it would mean the same thing. What's another way to say that and mean the same thing without saying this word afebrile or the translation of that, which would be without fever? Okay. It's another way of getting the same information across. Normal body temperature, exactly, okay, or some variation thereof. But if I'd said normal body temperature, then you would have understood it and it would have come up. So I just wanted to put something in there, this terminology, sort of to address that idea. Now, whether it's said this way, afebrile or normal body temperature or whatever, what does that tell us about what's going on in this case? Yeah, if there's no fever, the body's not fighting off an infection. Okay. So it helps us understand something about what's not happening here. It rules out possibilities. And that's what that bit of information is useful for. In the greater scheme of things, not a huge part of this case, but I put that in there for that aspect. Now, I want to look at the symptoms and signs in this case. So what is going on in the case? Okay, so he gets lightheaded. What's another way of saying that? Yeah, dizzy. Okay. What else is going on? Okay, so before the sweat, what was the other thing? What does that mean more specifically? Yeah, low blood pressure or hypotension, low blood pressure. What is normal blood pressure? Yeah, and what is his blood pressure? 86/67. Okay, so his is 86/67 compared to 120/80. It's low. Now, the 120/80 is our reference number. It's actually a cutoff above 120/80 is considered an elevated blood pressure. There's not a value that we use to say this is the cutoff for low blood pressure necessarily. In fact, it's probably better for your cardiovascular system to be a little lower than 120/80. 110/70, for instance, would be a much better blood pressure at rest for most people. It just means that the heart doesn't have to work quite as hard, that sort of thing, but it is lower, not clinically lower. It's just slightly lower than this number we're talking about here. Now, this guy, 86/67, the 67 isn't that low. Sure, it's a little lower than 80, but like I was just saying, 70 for the bottom number in blood pressure would be fine. So the 67 isn't really that low of a number, but the 86 is, okay? 120, 110, whatever, we'd expect the upper number in the blood pressure to be above 100. And so the fact that his is below 100 is definitely a significant drop in blood pressure, okay? And then, Kay, you said that he doesn't produce sweat, okay? What else? So what his heart rate is what? 72. Okay, 72 beats per minute. What's normal heart rate? Yes, that's an appropriate response, but I do want to modify that a little bit. You'll often hear 60 to 100, but a normal resting heart rate should be between 60 and 80. The 80 to 100 still can be an acceptable heart rate, but that's going to be a heart that's doing some work. Okay, if somebody's resting heart rate is around 100 beats per minute, then that's too high. But a normal heart rate, you usually hear the range 60 to 100, but 60 to 80 is usually a normal heart rate resting. So 72 is actually kind of right in the sweet spot there. 72 beats per minute is usually what we would expect to see. So that's pretty good. But I want to leave it up there, and we'll understand why in a little while. Okay. Anything else? Is that a symptom or a sign? No. That's just a fact. Anything else?
I was just wondering if he wasn't eating, maybe that's why he's like really white.
We're just looking at symptoms and signs here.
Is his weight good for his BMI?
I think if you look his BMI up, it's a little bit over the acceptable range. And I actually did that on purpose. It's like half a pound over the range. But it's an acceptable number. So, yeah. So an acceptable answer to anything else would be no. So, but I want to give everybody a chance to say something. Now, what we've done here is very similar to what would happen in pretty much any episode of House. Okay? And interestingly, my wife and I have just started rewatching the House series on Netflix. But it usually starts off early on where House's team is in his office and he's up at the whiteboard and they're calling out the symptoms and signs that they've come across for a particular patient, and they write them all down. Then they have to figure out from that what's going on. Now, this course is not about learning diagnostic tools or, learning diagnostic theory. I don't know where I was going with that one. I'm not teaching how to diagnose things here. It's about learning anatomy and physiology. So really, this is looking at functions that are lost. Okay. People shouldn't feel dizzy. So this person's normal, I don't know how to explain it, mental status, perception, whatever, is thrown off. They're having some problems. Blood pressure should be higher. Somebody, when they play basketball, should sweat a little bit, that sort of thing. So these are the functions that are lost. What we want to do first is to tie this to what systems in the body this is affected. Now, at this stage, I just want to look at what anatomy is related to these functions. I don't want you to start trying to solve what's going on here, but just which organ system is each related to. We want a picture of the anatomy that's part of this case. So when we talk about the symptom of being dizzy, what organ system is that actually a function of? Right. Okay. So as I was talking about this, I tried to kind of set it up by saying that his mental status or his perceptions are off. And those are nervous system functions. And that's the one I really have to get over. Everybody wants to try to find the cause for the dizziness right off. And that's not the point here. What about the blood pressure?
Cardiovascular.
Yeah, that's pretty obviously a cardiovascular thing. And what about the lack of sweating? Right. So sweat glands are in the skin, so that's integumentary. And I'm very impressed with all of you. Probably 9 or maybe 99 times out of 100, when I ask that, the response I get is endocrine. Okay. Now, since we will be talking about endocrine, I do want to pick up on that. None of you, from what I could tell, said that, but since it does lead into more of what we're going to be doing today later on, what does endocrine actually mean? Or at least what does endo mean? Into. The crin in endocrine means to secrete. So endocrine is to secrete within. Okay. But sweating, while it is secreting, it's secreting outside. Okay. So as far as relating to the word endocrine, sweat is an exocrine function. We don't have an exocrine system. Exocrine functions are tied into a number of different systems. And so this one specifically, sweat glands are in the skin, and so it's there. Now I'm not going to add for the heart rate because obviously that's also cardiovascular, and it's not really a symptom or a sign as we're considering it just yet. But that tells us what parts of the body are affected in this case. Now, in-house, what they're trying to do is get to a diagnosis. And the way it's portrayed is, they're established physicians. They've had careers, and they have the experience of looking at various things, various symptoms, and picking out what diagnoses would go with that for the characters. Now, of course, what's actually happening is those people are reading a script, and so they're being told what to say. Neither of those situations applies to you. Okay? You haven't been through medical school and in the medical practice for 8 years or something like that, and you're not reading a script. So I'm not asking you necessarily to find a diagnosis. In this case, the diagnosis isn't stated. And it's actually a little bit of a challenge to get to the diagnosis. And that's what I want to do in discussing this case. I want to lead us down that path to understand what's going on here. And in doing that, we'll understand something about how the autonomic system works. But inherent in what's happening, whether it's an actual doctor doing what's portrayed on House or the actors doing it and following the script, inherent in that is actually what we're talking about here. They look at those symptoms and they consider what all is affected in the body. And then they need to find an explanation to satisfy what one thing could have caused all of those changes. Now, like I said, my wife and I just recently started rewatching the series, and one of the early episodes in the first season, its title is Occam's Razor. Is anybody familiar with that term? Anybody heard that before? It's a very important principle in science in general, not just in medicine. It basically means, and so Occam is some sort of philosopher science, and so philosopher scientist. So he came up with this sort of simple way that scientists need to think about things to come to a accurate understanding of what's going on. I don't remember the exact wording. What I usually say to describe this, and actually let me write it down, is all things being equal, the simplest explanation must be correct. Okay. So what this is sort of a caution to scientists that they should not start jumping to conclusions and thinking up the most complicated explanation. What's going on with this guy is not that he was abducted by aliens and this is the result of his being anally probed or something like that. Because that assumes some very complicated and very hard things to prove, like the existence of aliens, or the connection between anal probing and sweat glands. Okay? That's a very complicated type of explanation. What needs to be the line of reasoning to try to figure out what's going on should simply be, what's the simplest explanation all these things have to do with? Now, in the episode that I'm talking about that's called Occam's Razor, if you've seen it, there's a nun who comes in presenting with first a rash and what looks like holes in her hands, which would be stigmata. And then she starts having a number of other symptoms. And so, just like I was saying before, they start off by writing all this stuff up on the whiteboard. Usually they make a list of things, but it turns out they were just sort of writing the symptoms up on the board kind of all over the place, which led to the way that they wanted to present it. They couldn't figure out one thing that made the most sense. And there's actually a little discussion of Occam's Razor in the show right there. And they start saying, well, it could be this, and so they call out a diagnosis, and House circles the symptoms that diagnosis covers. And then they say, well, it could be this, and he circles the symptoms that diagnosis covers. And they come up with like 5 different things. So he has 5 different groupings of the symptoms according to those 5 different diagnoses. None of them explains all of them, but from that he decides that 2 of them, if they're both happening at the same time, would cover the 5 or 7 or whatever symptoms that they have to deal with. And so that's where the Occam's Razor thing comes in. They're saying, no, it has to be just one thing, that the chances of somebody getting 2 diseases at the exact same time and presenting as a single thing is astronomically high. He goes into this kind of interesting little logical sleight of hand to say, no, it's more likely that this happened. But in the end, there is just one thing that happened. And they find that out and they, save the day. But House is trying to create drama that's going to last for 44 minutes, okay, to fill up the show. I'm not looking to be that dramatic or that interesting or having twists and turns. So Occam's Razor is a great understanding of what's going on here, because we want the simplest thing to be the answer. We don't want to get bogged down with, like, well, it could be this, or well, it could be that, or well, it could be such and such. A lot of people, like I said, when I'm trying to do this, I start off with what system is Dizzy responsible, is related to. And they'll start saying various things trying to solve the problem. But most of those answers don't take into account the other symptoms. So let's just try an exercise with that. What do you think could be causing somebody being dizzy?
Dehydrated.
Dehydrated.
Low blood sugar.
Low blood sugar. What else? Those are the only reasons people are dizzy?
Anxiety.
All right, I'll give you
Could be
an
hungry.
Nausea would be a co-symptom with dizziness. But both of those could be caused by what?
For blood pressure?
Blood pressure is not a possibility. You have a sense of balance or equilibrium. You're driving a car, you get car sick, that's dizziness and nausea, that's the sense of equilibrium. Okay. None of those things actually fit with the other things that are going on here. Now, it might seem like the dehydration does, because if somebody's dehydrated, their blood volume is going to be low, and therefore their blood pressure is going to be low also. And if you're dehydrated, then you're obviously not going to sweat. Okay. For what I've written up here, you can kind of make a case for that. But if you look at the case itself, if somebody's dehydrated to the point that they don't sweat, they're going to have bigger problems. They're not going to be able to play basketball. Okay? Their muscles won't work if they're that dehydrated. So it just doesn't fit with that, what actually is going on here. None of those things do. And that's because none of those things are really taking into account this idea of Occam's razor. Now, the easiest way for us to figure out what's going on with a case in this class is really to take advantage of something outside of the case, which is, why are we looking at this now?
Because we're looking at the endocrine and autonomic system.
More specifically, we're looking at what? Just the autonomic system. The endocrine we're doing in the second half. So this has to be a case about the autonomic system. So while it's not obviously in the case, the fact that we're looking at it now does give us a little hint that that's got to be it. Okay. And that helps to tie together these different systems. The autonomic system is part of the nervous system and can have effects on other parts of the nervous system. It helps control the cardiovascular system. It helps control secretions like sweat glands and that sort of thing. So that kind of tells us where we're going right there. Now, at this point, getting to the point to understand that this is a case about the autonomic system, I want to give you a little bit of a introduction to what the autonomic system is. At its simplest, the autonomic system is responsible for controlling homeostatic mechanisms in the body. In the book, as I'm talking about this stuff, there's a picture of a lioness here because another way of thinking about what the autonomic system does is one of the things it's responsible for is controlling what we call the fight or flight response. And so if you see a threat like a lion, you're going to either run away from it or you're going to stand your ground. Now, that doesn't happen to us on a regular basis. You probably don't run into lions too often. But I use that as an example because really for the human condition, for the physiological, biological, whatever history of humans, we've spent more time in an environment where that's a realistic threat than in an environment where we have the sorts of threats that we deal with today. How we respond to threats today is the exact same way that we responded to threats back then. So that's sort of my go-to example of what the fight or flight response is about. So if you see a lion on the savannah, you're going to have kind of a characteristic response to that. What's going to happen when you see that threat?
Oh my God.
That's going to be the end point. That's the flight and flight or fright. But what's happening to your body that gets you ready to run away from that threat?
Adrenaline.
So there's a surge of adrenaline through your system. What else is going on?
Doesn't your body switch to the way it can, the way you breathe
So
changes?
breathing changes. You're going to breathe
Okay.
more deeply and probably faster. What else?
Heart rate goes up.
Heart rate goes up. What's the heart rate going up for?
Cause you're pumping blood.
Pumping more.
Pumps more blood. And what does blood have in it? Oxygen, which we just got in by breathing faster, deeper. Okay. What else is going to happen?
Stop digesting.
If something's chasing you to eat you, you don't want to help it out by digesting some of the food in you. No, that's not actually the reason. No, your digestive system shuts down, but the reason why that actually happens has to do with blood. Okay. When you're digesting food, you want to get those nutrients into your blood. Okay. The nutrients that you get into your blood through the digestive system are not going to be any help to you at the exact moment that you're dealing with this threat. So the blood leaves the digestive system because it needs to go somewhere else. Where do you need that blood?
Your brain.
It needs to go to the brain, needs to go to the heart. Where else does it need to go? The muscles that are going to do what? Make you run. Okay. So blood vessels to those organs are going to dilate, and blood vessels to everything else are going to constrict. Okay. I usually concentrate on the blood vessels going to skeletal muscles for the running part, but it is true that the brain and the heart need oxygen too. Now, if you look at all of the blood vessels in your body, the ones that I just said dilate versus the ones that constrict, many, many more are going to constrict. And so that's going to actually systemically raise your blood pressure. Okay? And an increase in heart rate is also going to raise blood pressure. Okay? A very simplistic way of thinking about the cardiovascular system and changes in blood pressure that I like to use is to just think about a garden hose. Okay? If you want to have water coming out the end of the garden hose and shoot farther, the easiest thing to do is actually close down the end of the hose. Okay, think about, you're a kid and you're playing out in the yard with your kid sister and you're trying to soak her with a garden hose. You put your thumb over the end and make the opening smaller, and the water's going to go further and you're going to hit that little brat with the water. Right? That's the constriction aspect. Okay, so making the opening smaller, constricting blood vessels, increases the pressure, and so the water from the garden hose goes further, or the blood in your cardiovascular system moves. That's not a good way of putting it.
Flows faster.
Flows, well, no, it doesn't. That's not what actually causes it to flow faster. It flows where you want it more. Okay? So as pressure goes up in some vessels and it goes down in others, then the blood flows preferentially where it's needed. You can also think of increasing water flow in the garden hose just by adjusting the spigot at where the hose is attached to the house. So if you turn it up a little bit, you're going to get more water coming out, and that's kind of like increasing heart rate.
Does that do something to your muscles too, so she can run quicker?
You mean the fight or flight response?
Yeah.
What it does for the muscles is just getting more blood to it, so it has more oxygen and more energy to contract. Yeah. What other kind of things are going to happen? Fight or flight response. Can you see it there? So we've got rush of adrenaline, deeper, quicker breathing, heart rate goes up, blood is preferentially sent to skeletal muscles and other organs that need it. What else is going to happen?
Alertness.
So it's going to raise your alertness. You're going to pay more attention to what's going on around you. Your sensory systems are going to get more information in. One important aspect of that is for vision. Your pupils will dilate. Okay? You're running away from this threat. You want to see every potential obstacle in your course. Okay? So if there's a lump somewhere that you might trip over, you want to be sure that you get that information in. Now, when your pupil's dilated, it actually cuts down on acuity. A smaller pupil gives you better visual acuity. You can see what things are better, focus, that kind of thing. But there's a trade-off here between acuity and amount of visual information. So you want more light getting into your eye, even though it cuts down on your ability to see fine details. You're just trying to avoid that thing in your path. You don't care if it's a rock or a turtle or a bush or whatever. It's there. You just want to go around it. Okay? So that kind of thing changes also. So another thing that happens that people aren't necessarily going to think of is as you're about to run away really quickly, what's going to happen to your body? What's exerting yourself that much is going to cause what to happen?
Sweating.
No, it's not going to cause sweat. What happens when muscles contract a lot?
Lactic acid.
You're going to make lactic acid, which is going to move away because your blood flow is pretty good to muscles. But what else is going to happen? Okay, so they're going to fatigue. What is at the root of muscle fatigue? Why do muscles fatigue? And shame on you for if you had me for AP1, because that was one of the questions I
I mean,
specifically asked.
because aren't muscles supposed to be contracting, relaxing, contracting, and relaxing? So if
They
just
are.
keep contracting, like,
No, every step you take, you contract some muscles and relax others, and then it switches off as you go to the other leg. So they're going back and forth. But what are they doing to contract? What do they need to contract?
Sodium?
Not to contract. Calcium gets it started, but what do they use up when they're contracting?
ATP.
ATP. Okay. What happens when you break down ATP chemically?
It makes ADP.
Right, so ATP to ADP and an inorganic phosphate, that reaction, what comes of that reaction?
Heat.
Heat, right. So when you're exerting yourself, you're going to start to heat up. And so how do you deal with overheating?
you sweat.
That's where the sweat comes from. Exerting yourself doesn't cause a sweat. Sweating is our way of maintaining body temperature. Okay. And that's actually another part of the fight or flight response. Because you're about to start exerting yourself, you go ahead and start sweating along with all that other stuff. Okay. It's going to make it possible for you to stay cool while that's happening. Okay. So I'm couching all of this in the idea of the lion on the savannah, which is not actually something that happens to us too often. But if you think about modern threats, you're still going to have the same kind of responses there. So if your job has you working in a cubicle 9 to 5 or something like that, which obviously not because you're here, but think of that kind of thing. It's Friday afternoon, 4:45, you're looking forward to the weekend, and suddenly the boss starts walking down the aisle between the cubicles. That's the same kind of threat, psychologically speaking, and so your heart rate's going to go up, you're going to start breathing differently, et cetera, et cetera. You're going to start to have sweaty palms and your forehead might start sweating, that kind of thing. All the same kind of thing is going to happen. Not necessarily to the same extent, but you're either looking for a place to run away and avoid that threat, or you're trying to figure out how to stand up to that threat and say, nope, got to go home this weekend. So whatever it might be. So that's sort of the idea of at least part of what the autonomic system is about. I started by saying it's really about controlling homeostatic mechanisms, but really what it does falls into 2 different categories or 2 different divisions. There's the sympathetic division of the autonomic system and the parasympathetic division. Okay. Now, the word sympathetic, you've probably heard that, you probably use it plenty, means essentially with feeling. Okay, so usually when we think of somebody who's being sympathetic, it's like, your friend just lost their pet hamster and you're sympathizing with their loss, something like that. You're feeling with them. Sympathetic for the division of the nervous system means with feeling to some degree also, but instead it's really referring to the fact that besides controlling autonomic stuff and being in charge of something like the fight or flight response, it's tied to our emotional reactions. Okay. So if we're anxious or excited or there's a third one I usually throw in there. No, that's completely different. There's another emotion that usually fits in with it, excited or anxious or excited. There's a third one, I can't remember what it is. I usually say that. But those responses are kind of all those same things. Heart rate goes up, you might get sweaty palms or something like that. It's the fight or flight response. And so that's what we really mean by sympathetic. We're talking about the sympathetic vision. It's tied into those emotional responses. Now what I have up on the board there is a depiction of the anatomical connections of this system. Now, not the whole thing. What we're talking about here are reflex responses. Okay? So if you see the lion, your reflexive response is a fight or flight response, something like that. But we can look at the specific things going on, and it's not just about responding to threats. There are reflexes built into all this that are homeostatic mechanisms. We're actually just looking at the output side of the reflex. And the sensory input isn't terribly important to what we're talking about here. So we're just really paying attention to the output. And that's what this picture is showing us. The sympathetic nervous system starts with output that's found in the thoracic and upper lumbar regions of the spinal cord. And then, so if you look at this picture, there are little dots right there through T1 through about L2 or sometimes L3, depending on what source you're looking at. Neurons located in the spinal cord are going to send axons out into the periphery to have an effect. Their targets are ganglia, groups of neurons in the periphery. In this model here, they have those ganglia depicted running alongside the spinal cord here. It's called the sympathetic chain ganglia. It's a chain of ganglia for the sympathetic system. There's actually one on either side, but for the sake of this model, they only show it on one side. Some of it is obscuring view of other stuff that this model is showing. But there are two, and that's what's depicted over here. For the sake of the drawing, they've drawn in both chains, and you can see connections from the spinal cord out to the ganglia on either chain. But instead of drawing everything on both sides of the picture, they're just showing the connections from the chain ganglia out to one side of the picture. Some of these targets are unilateral is not exactly the word I want to say, but for instance, the heart. You only have one heart, okay? So we see a connection there. There are connections coming from both sides because the heart, of course, is not out to that side of the spinal cord. The heart's a little bit anterior to the spinal cord. And so there's going to be connections coming from both sides going to the heart. Probably a little bit more on the left side than the right side because the heart is a little bit off to the left side, but there will be bilateral connections to it, even though there's only one of them. Or the esophagus, which we have in the picture, the stomach, et cetera, et cetera. There are only one of each of those organs, but there are actually connections from both sides to them. For the sake of this picture, they're all drawn off to the side of the picture, so the connections are only depicted coming off of one side, but really there's connections from both sides. On the other side of the picture, what's drawn in there is a little patch of skin. It's kind of a line drawing version of the picture that's in the skin chapter back in A&P1 that showed you, the epidermis and the dermis and that sort of thing. There's a hair follicle in it, that sort of stuff. But it's just showing you the skin. There are projections from the sympathetic system to the skin. What's relevant to this case is controlling sweat glands. So that's how spectacle's controlled. It's only showing it coming from one spot for the sake of making a picture simple, but of course you have skin all over your body, so there are going to be connections from all different areas going to the different parts of your skin. So from this area right here, which is at the T8 level in the picture, it's going to a patch of skin. Let's see, where would T8 be? Right about here, probably. And if we go up to, say, the T1 area there, that's going to go maybe to the shoulder area and armpits and that sort of thing, et cetera, et cetera. So those nerves are going to be connected out to the skin at specific areas in an anatomical arrangement, just like your sensory system works there. It's just depicted in one little spot in the picture. For the sake of this picture, the axons that go from the spinal cord to the ganglia are depicted as solid lines. And then axons that go from the ganglia to the target organs are depicted as dotted lines, because there's two axons that we're talking about here, two neurons involved in this. There's the central neuron in the spinal cord that projects out to in synapses at the at the ganglion. And then there's a neuron in the ganglion, which is the target of that first cell. And its axon goes out into the periphery to the target organ and connects to the target organ. The axon from the spinal cord to the ganglion is referred to as the preganglionic fiber, or sometimes you'll hear preganglionic neuron, although I prefer to just concentrate on the fiber or the axon part of it. And then from the ganglion out to the target organ, we call that the postganglionic fiber. So in this picture, the solid lines are preganglionic fibers and the dotted lines are postganglionic fibers. And you can see dotted lines here going to the eye and other structures in the head, or here going to the heart and esophagus. You might say, wait a second, those are solid lines coming out of those ganglia. But actually what this depicts is the preganglionic fiber that starts in the spinal cord goes out past the chain ganglia to another ganglion outside of that chain. So this circle here, and this circle here represent three other ganglia that are part of the sympathetic system that are not in the chain, but they're other ganglia. So they're depicted there. And then from that, we see dotted lines going out to the targets. And hey, this is cool. The website updates pictures, updates the book on a regular basis, and I just noticed that they corrected a really big problem. Notice that there's this one solid line right here, which means that that's a preganglionic fiber. Okay? So a neuron, somewhere in here, its axon comes out past the chain ganglia, goes through this ganglion, but doesn't synapse and keeps going on till it gets here. Okay, and what this is depicting is the adrenal gland. Okay, now what did we say earlier about what happens when you see the line on the Santa that has something to do with the adrenal gland?
Does it amp up somehow?
But what does it amp up? Adrenaline. Adrenal gland, adrenaline. That's what adrenaline is named for. It comes from the adrenal gland. The adrenal gland has two regions. The inner part, called the adrenal medulla, makes adrenaline. The outer part, called the adrenal medulla, makes a bunch of other signaling molecules, which we're going to talk about with the endocrine system later on. Okay. Anyways, so I'm very excited to see they finally fixed this picture. They used to have a dotted line here, which was just completely wrong, but it's in fact a preganglionic fiber that goes to the adrenal gland, because the adrenaline that's released from the adrenal gland is essentially the same chemical that's released from the postganglionic fibers onto the target organ. Okay. Now, the name of the neurotransmitter that's released from those axons is a little bit different from adrenaline, but it's really the same thing, or well, it's effectively the same thing. If we look at the word adrenaline, okay, the root, renal, or rene really, refers to the kidneys, okay? Because where do we find the adrenal gland? Sorry? Not in the kidney.
That's here.
Near the kidney, but more specifically where? On the kidney, on top of the kidney. And that's what ad means. Oh, keep going. There are some sources that are starting to call the adrenal gland the suprarenal gland, which really bothers me because adrenal means basically the same thing. But now this comes from Latin. Okay, adrenal means on top of the kidney from Latin. A drug company back in the 60s started making a drug that was adrenaline. And by making it, I mean they got it from some natural source somewhere, and they packaged it up and sold it. Because they were selling adrenaline as a drug, they decided that they'd go ahead and trademark the name adrenaline, because it's part of how they did business. In doing that, they made things a little bit uncomfortable for your average researcher. Somebody's studying the effects of adrenaline in the body, independent of what the drug company is doing, but just studying adrenaline. If they wanted to publish a paper referring to adrenaline, adrenaline's now a trademark word in the United States, they had to get permission from the drug company. Now, the drug company might probably have said, oh, no, that's fine, science can use the word, they want to publish, but they always had to ask first. They had to get written permission to use a trademark. And this is very troubling, because if the drug company ever got to a point where a scientist wanted to publish a paper about adrenaline that would potentially interfere with the drug company's business of selling adrenaline as a drug, they might say, no, you can't use that word, we have a trademark on it, and then the paper would never get published. So science had a very inventive way, which is to switch languages. Okay. So I told you a second ago that ad means on top of. In Greek, epi means the same thing. Okay. And then rene, or renal, refers to the kidneys. In Greek, nepher is the same root. Okay. A nephrologist is somebody who studies the kidneys. Okay. And then if we put ine on the end of this word, just like on the end of adrenaline, we have epinephrine. Okay. Epinephrine is the exact same thing as adrenaline. Okay. Different word for the same thing. It helps scientists get around that trademark issue when they're publishing papers about it. Okay. Now, you've probably heard of epinephrine, or more likely, the EpiPen or something like that. So the companies that sell the EpiPen, they can't trademark the word epinephrine, so they probably trademark Epi or EpiPen or something like that. But it doesn't cause the same problems, because people are not going to refer to epinephrine in that trademarked way anymore. I don't think that the drug company that trademarked adrenaline still sells a drug called adrenaline, but they still own that trademark, I believe. So we still use epinephrine. In scientific literature, sometimes this chemical is referred to as adrenaline, and sometimes it's referred to as epinephrine. It's not always terribly obvious about when that happens, but it's actually a fairly simple rule. United States scientists publishing will use epinephrine. Anybody publishing science outside the United States will use adrenaline. So you'll hear reference to epinephrine and adrenaline. In the United States, we use the word adrenaline in common usage to talk about epinephrine, because you can't enforce trademark on just common usage of words, which is why we call things Band-Aids or Kleenexes or something like that. But in formal writing, epinephrine will be referred to as adrenaline. Now, the actual neurotransmitter that's released by postganglionic fibers in the sympathetic system is actually called norepinephrine or noradrenaline. The prefix nor is simply a chemical designation that means something minor that I don't really care about right now. For our purposes, there's not really any difference. Adrenaline or noradrenaline, epinephrine or norepinephrine, all have the same effects in your body. The adrenal medulla releases epinephrine. Postganglionic sympathetic fibers release norepinephrine. The receptors that they bind to on their target organs don't distinguish between those two molecules. So they're both going to have the exact same effect. So on the heart, there's a receptor for epinephrine or norepinephrine. Either one can bind to it, and it's going to cause the heart rate to increase. Okay, so they have the same effect. So back to this picture real quick. I'm very excited. This is the first time I've pulled up this picture, and that's been corrected. It used to be a dotted line, but that is a preganglionic fiber that goes to the adrenal medulla, really. And that's going to release epinephrine into the bloodstream, which is going to have the same effect as the norepinephrine that's released directly onto any of the target organs by these postganglionic fibers. Okay. Now, I go into talking about the neurotransmitters that are involved in all this stuff in a little bit more detail in the book. But I wanted to point that part out because, one, I wanted to explain the epinephrine adrenaline thing, and also to point that out. And that kind of gives us a picture of the sympathetic division. Now, if we go down in the book a little bit further on, here's another picture in the parasympathetic division section. And it shows a similar picture. Here we have that same part that we just looked at for the sympathetic side. But for the parasympathetic stuff, the preganglionic fibers are coming out of the brainstem or the sacral spinal cord, and they're going out to synapse at ganglia that are right next to the target organ, or in fact, in the target organ itself. So I'm just zooming in here. So here's part of the picture where we see a preganglionic fiber reaching a ganglion, and then postganglionic fibers going to the target, which happen to be components of the salivary system there. Or here we see a preganglionic fiber synapsing on something that's pretty much in the wall of the heart, or pretty much in the wall of the respiratory tract, or pretty much in the wall of the digestive tract. Okay. Parasympathetic ganglia are located at or near the target organ, and they're referred to as terminal ganglia. Okay. Terminal meaning at the end of the line. Sympathetic system, it's the chain ganglia, or those three special ones that are not right at the chain, that are closer to the spinal cord. And for the parasympathetic system, the ganglia are at or near the target organ. Okay. There's sort of a difference there. Now, in this picture, they have depicted still the preganglionic sympathetic fibers and the sympathetic chain ganglia and a little piece of skin still in there. This is all drawn in red lines depicting the sympathetic side, but the picture here is really stressing the parasympathetic connections. Now, I said that sympathetic is referring to the fact that the sympathetic responses are tied into emotional responses like anxiety or excitement or something like that. Parasympathetic that word is used to describe the anatomical relationship between the two systems. Para means around. So while the sympathetic system starts in the thoracic and upper lumbar spinal cord, the parasympathetic is partly above that in the brainstem and partly below that in the sacrospinal cord. It's parasympathetic, it's around sympathetic system. When I was talking about the emotional responses, I'm just trying to think of the third one, which still hasn't occurred to me yet. Somebody said sad. Yes, that is an emotional response. But really, depression is often more tied into parasympathetic activity. And that's not a really easy thing to describe because really what's going on in depression is a lot of that's happening in the brain. And it has a lot to do with the neurotransmitter serotonin in the brain, as well as a couple of other things there. And I mentioned serotonin because sort of the primary antidepressant drugs work on the serotonin system. The parasympathetic system pretty much exclusively uses acetylcholine as its neurotransmitter. Where did you first learn about acetylcholine as a neurotransmitter? Right, it's at the neuromuscular junction. Okay. Where are the neurons that control muscle movement, that actually make muscles contract? Where are those neuron cell bodies located? I'm just going to say no. I know you, and I know you're just trying to guess there, but where's the cell body located that causes my biceps brachii to contract?
The fibers.
So there's a fiber that's connected there, but if we follow that fiber back, where did it start? Insert. Oh, no. That's where the muscle starts. I'm asking where the nervous control of it starts.
Brain, spinal cord?
Spinal cord. Okay. The brain is going to tell the spinal cord what to do, but then the spinal cord is the one that actually controls contraction. Remember the motor unit? A neuron connected to all these muscle fibers. The motor unit neuron is located in the spinal cord, specifically in the ventral horn of the spinal cord. And it releases acetylcholine at the neuromuscular junction, causing contraction. For the autonomic system, if we make a cross-section through the spinal cord, wherever we're looking, the neurons that are the preganglionic ones, the ones that are going to connect out to the ganglia, they're located right next to the ventral horn in a region called the lateral horn of the spinal cord. And they travel alongside the same nerve fibers that are going out to the muscles, and they release acetylcholine. Okay. Now, I'm talking about all autonomic fibers leaving the spinal cord. So that's parasympathetic and sympathetic fibers. All preganglionic fibers release acetylcholine. Okay. And they're almost indistinguishable neurons from the ones that control muscle cells. Okay. They're anatomically similar in structure and location. They're physiologically similar in what chemical they release, all that stuff. The postganglionic fibers are different. Okay. I was saying earlier that the postganglionic fibers for the sympathetic side release norepinephrine. The postganglionic parasympathetic fibers release acetylcholine. Okay. So let's say you're the heart. The only way you know what to do to beat faster, to beat slower, is based on which chemical is released onto you. Okay. You have receptors for norepinephrine, and you have receptors for acetylcholine. Okay. Whichever chemical is released binds to its receptor and causes the heart to increase or decrease activity. Okay. That's the connection there. Now, I'm kind of going off a bit more on a tangent, not tangent, but a little bit more depth than I was really planning on, talking about the connections and what's controlling things in the system. But I really kind of wanted to get into a lot of the stuff that has to do with how the autonomic system works. The book goes into that in a little bit more detail. And I wrote this chapter in the book, so it's going into the detail I want you to know about this. But I want to get back to the case study and keep talking about that. However, while I kind of went off on talking about those connections a little bit, it was important to understand a little bit about what's going on. Mostly in what we started talking about, where connections are here. Now, if we go back to the symptoms, there's one symptom, well, actually kind of in a way, two symptoms that tell you exactly what part of the autonomic system is having problems in this case. Which symptom tells you that?
No sweating.
Why?
Because when you sweat, it's cooling your body. So it's gonna affect your blood pressure.
Well, okay. You're doing so well with
It's visible.
So as we talked about a little bit ago, during the fight or flight response, you start sweating to help cool down your body. Part of that response, which I was describing, and that's the sympathetic response. Okay? The fact that he's not sweating suggests that his sympathetic system isn't doing the job it's supposed to. Now, also, and I didn't make a big point of saying this exactly, but it's true, this picture, which is showing the sympathetic connections, I did point out there's that little patch of skin represented on the other side of the picture. In the other picture we were looking at, for the parasympathetic side, they still have that drawn in, but I said that it's only drawn in red connections representing the sympathetic side. There's no blue connections, there's no parasympathetic system connection to the skin to control sweat glands. Okay. For sweat glands, it's just an on-off switch. Okay. They get a signal, they produce sweat. They don't get a signal, they don't produce sweat. So they only need one input. Something like the heart needs two inputs because the heart beats and the sympathetic system tells it to beat faster and the parasympathetic system calls it to beat slower. Okay. Your pupils are at rest a given size. They can open up wider, they can dilate more, or they can constrict further. So they need the sympathetic side to tell them to dilate, the parasympathetic system to tell it to constrict, but normally just sort of sit in the middle. Most systems have this kind of dual input. The sweat glands are an exception to that. Okay. There's only sympathetic input to the sweat glands. Now, that's the perfect example of how we can tell from this case that it's sympathetic. Okay. If this case was based on parasympathetic problems, there would be nothing related to sweat, because the parasympathetic system just doesn't control sweat glands. But as I was setting that up, I said there's actually two things in this that point to this being sympathetic. The other thing is the blood pressure. What should the sympathetic system do for blood pressure?
Raising it?
Raise it. And he has what?
Low.
Low blood pressure. So his blood pressure is not doing what it's supposed to do. Now, the dizziness is related to that also. We've established that two of the three things we're talking about are sympathetic system. And so again, back to kind of thinking about the Occam's razor idea, the simplest explanation is that the other thing we're dealing with here is also going to be caused by that. And in fact, it is. It's pretty easy to see that. Why is he getting dizzy?
He's not getting enough blood to the brain.
Why?
Because there's nothing.
Very low.
Blood pressure's low.
No,
And why is low blood pressure going to make it hard to get blood to the brain?
You gotta pump it.
Well, it doesn't open up cardio.
What does it have to pump against?
Gravity.
Gravity. Right. Look back at the case. When did he get dizzy?
When you're saying, oh, in the morning.
When you woke up in the
First thing in the morning and occasionally throughout the day. Okay. What does occasionally throughout the day mean?
His blood pressure is fluctuating.
Probably when you stood up.
It doesn't mean anything. I mean, at best, it means it's
It's
fluctuating
just
throughout the day.
something you know.
But you have to ask questions because patients don't give you all the information you need. So you could, if you asked him, what do you mean by occasionally throughout the day? He would have said, well, I'm a retail manager. Half my job, I'm in my office at the computer. Half my job, I have to go out on the sales floor and look at my sales staff. And pretty much whenever I'm going out to look onto the floor, when I'm leaving my office, I always have to stop for a second and kind of steady myself against the door jamb or I'm going to fall over. So I feel a little dizzy right there. That's when he actually is feeling dizzy occasionally throughout the day. So what does that tell us about that? Now that tells us a lot.
Is he not getting enough fluids?
No? We've already established that it's
Blood pressure is
He's
always low.
standing up.
because he's standing up from his office chair. And as he's leaving, he gets a little woozy. What is it? No. So we just established that the heart needs to pump blood harder against gravity when he gets up in the morning, when he stands up from his desk. That's why he's getting dizzy. Okay. That is a sympathetic reflex. Okay. Does anybody know what we call that condition when somebody gets dizzy when they stand up?
Vertigo?
No, that's when your sense of balance is off. Orthostatic hypotension, right. Hypotension means low blood pressure. What does orthostatic mean?
Is it like when you're sitting, laying, and standing?
That's how you test it. Okay. So if we took this guy and we took his blood pressure when he's laying down and when he's sitting up and when he's standing up, we'd see it drop. Okay. Laying down, it's probably fairly close to the 120/80 normal thing. Okay. But as his body position changes, it's going to drop. Orthostatic, best as I can sort of describe what it means, ortho means right, as in a right angle. Okay. And static is the root that we get words like stand from. Okay. So if you're standing at a right angle, you're upright. That's kind of what orthostatic means. Not a perfect definition, but it's kind of taking the word apart. But that's what's happening for this guy. Okay. Now, that is not his definition. That is not his diagnosis. That's really what ties the dizziness and the low blood pressure together. But it doesn't get at the sweat problem. Okay. To figure out what's really going on, we need to do a little bit more work. So the easiest thing to do is to go where any hypochondriac would go, which is the internet. So if we put orthostatic hypotension and no sweat into a Google search, we'll get a number of hits that'll talk about things going on here. So this first one here, just eMedicine, medscape.com, just talking about the sorts of things that can cause this. So the title of this article is Idiopathic Orthostatic Hypotension and Other Autonomic Failure Syndromes. Okay. What does idiopathic mean? Yeah, it's, idio is where we get the word idiot from, which is not really why it means that, but it means they don't know the cause of the disease. That's what idiopathic really means. But it just sounds better than like, I don't know. Now in this article, they describe the sorts of things that could lead to this. So kind of the same thing as this title up here. The first thing they put is idiopathic orthostatic hypotension and other forms of pure autonomic failure. It's not exactly the same thing as the title because pure autonomic failure is not just other autonomic failure syndromes. It's the ones that are purely affecting the autonomic system. The other ones are listed here, multiple system atrophy and autoimmune autonomic neuropathy, are also autonomic failure syndromes, but they have more specific, or not more specific, better understand causes, okay, to some degree. So autoimmune autonomic neuropathy, autoimmune means that the immune system is reacting to something in the body. That's what's causing it. Multiple system atrophy is a autonomic failure syndrome, but it's not pure. It has other neurological components to it, other problems with the nervous system. Okay, that's what it's getting at. They go in to talk about the sorts of things that we'd see here. Signs and symptoms, orthostatic hypotension, we talked about that. Decreased sweating, we talked about that. Ejaculatory dysfunction, not in our case. Ptosis associated with Horner syndrome. Ptosis means the drooping eyelid, which some of you might remember from last semester. Horner syndrome, it's a series of symptoms associated with the condition. A lot of them, for some reason, have a lot to do with what's going on with the eye, that kind of thing. All of those are sympathetic related problems. And we already know our guy is sympathetic, and the first two things listed there are essentially what our case is about. Okay. I used to have a version of this case that included ejaculatory dysfunction, but I took it out for an interesting anatomical reason, which I won't get around to explaining to you, but it's it used to be part of this case. You can also have parasympathetic things, and whoops. So there are a number of different things listed here, but none of those have to do with our case because our case is not parasympathetic. Okay. Then they kind of repeat themselves talking about pure autonomic failure here, except they're not separating this list into sympathetic and parasympathetic things. They already did that up here. Why they didn't keep it, I don't know, but they didn't. And then for the other two, they basically say you'd see the same stuff here plus other problems. Okay, so for the autoimmune version, there's sensory abnormalities, pain, and loss of certain types of reflexes. How do we know that's not in our case? What does our case tell us that rules this out?
He's playing basketball. Well, he was playing basketball.
Well, he could play basketball with this too, I suppose. Might not be very good, but there's something specifically in the case that rules this out.
He has no other complaints.
And specifically, what else? What specifically, what is there a lack of that points to this?
There's no fever, pain. Medication?
Well, pain and fever are not the same thing. I was getting at the neurological signs. So pain, reflexes, and sensory abnormalities would all show up in a neurological exam, and it said specifically that didn't happen. For the same reason, we can rule out multiple system atrophy because besides what is present in our case, it would also present with motor dysfunctions. And there's no sign of that there. For some strange reason in this article, even though they don't talk about it up above, they throw in another one here that has to do with another orthostatic type thing, but it's not nearly, or it's not what our guy's going on with, because the drop in heart rate described in this is, no, wait. There is a drop in heart rate described in this. Our guy has normal heart rate. Okay. Now, the fact that he has a normal heart rate actually is another sign that something's wrong. If you have low blood pressure, your autonomic system will respond to that by both constricting blood vessels to raise blood pressure directly and by increasing heart rate. Because as the heart beats faster, blood pressure goes up too. His heart rate's normal, 72 beats per minute. If he has low blood pressure like that, he should have an elevated heart rate to compensate, and he doesn't. And that's because the heart rate and blood pressure thing are both controlled by the sympathetic system, and that's where his problem is. So, Now, if we search for more information about pure autonomic failure specifically, it used to be the top hit in this search, but it's now fallen to number 2. But this is an article about pure autonomic failure at the Vanderbilt Universal Medical Center. They have a research group that focuses on autonomic dysfunctions. And so they have some information here. This is actually the source for the case that we're working on. I read this article and I created this case. It does explain a little bit about what's going on here. And it does fall under the idiopathic description a little bit, because it's not clear on exactly what's causing it ultimately. But the main problem is there's a loss of cells in the intramediolateral column of the spinal cord. Now, as an anatomist, I hate the word intramediolateral because it doesn't really mean a whole lot. Inter means between, and then mediolateral is 2 ends of a spectrum. So from midline to the side. And so they're saying somewhere in the middle to the side, there's loss of neurons. Specifically, it's that lateral horn that I talked about a second ago. That's in this area, but lateral horn is a much better way of saying that. This is just a very vague term here. But cells are dying off there. Now, it goes on to say that multiple system atrophy, which is one of the other diagnoses that article I just showed you talked about, and Parkinson's disease are related to this disease, related to what causes it. They all kind of work the same way. We don't know what actually causes any of them, but they all have the same basic problem, which is this toxic molecule called alpha-synuclein is killing neurons. Now, alpha-synuclein is an interesting toxin. Well, the fact that how it works is kind of interesting. Usually when we think of toxic molecules that are causing things to die off in the nervous system, we usually think of you introducing something to your brain. You've probably heard lots of people talk about, oh, you do that, you're killing brain cells. You drink too much, you're killing brain cells. You take drugs, you're killing brain cells, et cetera, et cetera. You think too much, you're killing brain cells. Actually, if you think too much, you do kill brain cells, but that's beside the point. We usually think of things causing brain cells to die because we're taking too much of something. Alpha-synuclein is an example of an endogenous toxin. Now, there is a molecule called synuclein, which you have a gene for in your genome, and you make the protein in nerve cells. What that protein actually looks like, I have no real idea. But let's say I folded up that synuclein molecule. What happens with alpha-synuclein toxicity is the protein starts to change shape. Something happens. And this is the part we don't understand. This is the idiopathic part of it. Something changes that protein, and it's no longer the same shape. When proteins change shape, they change function or lose function. So the normal synuclein, which I think is called beta-synuclein, or it might be gamma-synuclein, has some important function in the nerve cell. But when it changes into alpha-synuclein because something has caused it to change, the neuron stops functioning properly. And the default in the nervous system when neurons stop working the way they're supposed to is that they die. Neurodegenerative disorders are fairly devastating and fairly well known. Parkinson's disease, Alzheimer's. MS is not about neurons dying, it's about myelin dying. But yeah, it's still going to have a devastating effect. So degenerative disorders in the nervous system are really big things to deal with, and this is one of them. So this molecule causes toxicity and these cells die off. And when the cells die off, in the lateral horn of the spinal cord, then you're going to start losing the sympathetic functions like producing sweat or controlling blood pressure when you stand up. So that's sort of the root of what's going on. Now, in talking about this case, I wanted to illustrate the idea of thinking about how to read a case study and get some information about the functions and structures that are involved in it to connect it to the basic anatomy and physiology, which is kind of what I was laying out here. And you can take that to look at the other cases here. Okay, so we were just looking at case 1. You can look at cases 2, 3, and 4 and approach them the same way to understand what's going on there. You'll need to do that in preparation for the practical exam, which is week 5, I think it was. So I'm not saying this is something you need to do this week. It's not homework for next week or anything like this, but it is something that you're going to need to take some time to do. Case 1 of these 4 cases here is the tough one to understand. I didn't put enough in there to really explain the diagnosis because I spend time talking about it here in class. But case 2 says right off the bat she has diabetes. That's the diagnosis there. Case 3, it's a guy going into the hospital because he has chest pains. And I can't remember offhand if it's a history of or markers for heart attack, something like that, but it's a heart attack case. And then case 4 is about a guy that goes to South America and comes back with more friends than he anticipated. Very, very, very small friends. Okay. And it's pretty clear from the case what I'm talking about. So the other 3 cases are very upfront about the diagnoses. This first case here isn't, but I kind of showed you how I can get to that by looking at the case, the symptoms. It's just your basic Google search for the symptoms, orthostatic hypotension, no sweat, and pointed us right to a article that explained autonomic failures and the 4 big diagnoses there: pure autonomic failure, autoimmune, autonomic neuropathy, multiple system atrophy, and then the last one about the heart rate thing. 3 of those we could rule out. Okay. That's what House does. They come up with possible explanations and they say, no, can't be that. We don't see those symptoms. Can't be that. Doesn't explain that symptom, et cetera, et cetera. So we ruled out those other diagnoses, and all that was left over was pure autonomic failure. And that's what's going on. Now, in that article about pure autonomic failure, it's abbreviated PAF for pure autonomic failure. I want to warn you that there are other things that are abbreviated PAF. So if you're looking up abbreviations, make sure that the abbreviation is relevant to what you're talking about. This is obviously an autonomic case, so PAF is the abbreviation that has to do with the autonomic system. So, okay, that got to wrapping up what I want to talk about with this case, and I got to talk a little bit about what the autonomic system is. I am going to refer to a few things that'll go back to the autonomic system a little bit when I talk about the endocrine system in the second half of the day, but I think I hit on the big things. And again, the chapter on this is, I wrote this chapter. In doing that, I'm basically giving you the kind of information that I want. You to understand about this, and that's really tailored to the assignments that you have for this stuff. Any questions at this point? Okay, so let's go ahead and take a break. I'm a little late on taking a break, but that's fine. So about 20 minutes, we'll be back in here at 10:20, and we'll look at the endocrine system stuff.